In a typical development pipeline, the entire deployment process can halt because a developer changed a single front-end CSS ID from submit BTN to login BTN. But in a modern autonomous setup, that same missing identifier triggers a different response. The system identifies the discrepancy, flags a warning, and continues the test without a crash. The system uses computer vision to interpret the screen, recognizes the functional intent of the original script, executes the action on the new button, and updates the test repository code in real time. Brittle UI dependencies are becoming a secondary concern as these autonomous layers take over the task of maintenance. As of May 2026, enterprise architectural standards are moving away from the maintenance of manual post-compilation testing frameworks. Engineering teams are instead allocating their resources to autonomous quality assurance layers that operate before and during execution. This strategy utilizes two distinct paths: runtime DOM analysis to maintain user interfaces, and pre-compilation analysis to identify back-end logic errors before the code is even built. In this model, testing is an autonomous property of the development architecture rather than an external phase applied to finished code. Engineering teams have historically spent significant time fixing flaky tests, where minor cosmetic changes to a UI cause massive automation failures. These failures happen because legacy test scripts are often mapped to rigid CSS IDs. When a string of text changes, the script no longer knows where to click. To solve this, we use the DOM to view the interface as a hierarchical tree of nodes. An AI analyzes this structure, identifying elements by a cluster of attributes like size, relative position, and neighbors, rather than a single ID. Replacing hard-coded locators with structural context makes automation resistant to localized styling or naming changes. When an expected ID is missing during a test, the system triggers intent recognition. The agent reads the current state of the application to infer exactly what action the script was trying to perform, such as submitting a form or opening a menu. Using visual heuristics, the agent finds the functionally correct element and executes the required action. The agent autonomously rewrites the source code in the test repository to match the new UI structure, removing the need for human intervention. Test maintenance becomes a continuous runtime task, minimizing pipeline downtime caused by routine UI updates. On the back end, the concept of shifting left is evolving. It traditionally meant writing unit tests earlier in the sprint. The current standard involves analyzing uncompiled code in real time while the developer is still typing. This real-time analysis is made possible by the Abstract Syntax Tree, or AST. As you write, AI converts text into an AST, a mathematical tree structure representing the program's logic. It compares your current AST against millions of historical branch patterns. This identifies structural vulnerabilities, like memory leaks, by recognizing the shape of historically failed code. Logic errors are identified through mathematical prediction based on historical patterns, rather than through trial and error execution. When the system flags a vulnerability in the AST, it immediately initiates a resolution cycle. The agent generates a unit test to prove the specific vulnerability it just predicted. It writes a logic patch to resolve the error. This cycle happens before staging, or even compilation. While runtime verification is still necessary for environment-specific issues, predictive patching ensures that the core logic is mathematically sound before the binary is ever created. This integrated loop of AST analysis, predictive patching, and DOM evaluation forms the backbone of the modern pipeline. To manage these autonomous agents, we have introduced a critical governance component, the guardrail layer. This layer holds the safety metrics and performance parameters that every autonomous change must pass before it is merged. These metrics ensure the AI does not introduce non-compliant or unverified code into the production environment. The engineering focus has moved from the manual discovery of bugs to the governance of the AI agents that fix them. Writing manual boilerplate tests is no longer a viable long-term career path. Industry demand has shifted toward the role of the quality architect. For students and engineers, this means pivoting your focus towards static code analysis and the structural mechanics of ASTs. Priority should be given to learning how to design the safety metrics and CI/CD guardrails that govern autonomous systems. The highest paid roles are now held by engineers who can architect these governance protocols. Software quality is an autonomous architectural layer. Future-proof your career by building these systems, rather than manually operating the scripts they are replacing.